math you need for computer science. I mean, come on. We are on episode 7 called Numbers here, and this episode is gonna crack you up, okay? Because it's gonna seem just amazingly simple when we first start. You're gonna be like, huh? This is a college class? It's gonna seem insultingly basic. And yet, there's gonna be a point or two when you are going to be understanding everything, and this is going to be like stuff that you've known since before you could read, literally, and then suddenly, without warning, all the rails are going to come off. And you're going to be like, wait, what? Rewind the tape? Did he say that? That must have been a mistake. And then you'll go on and realize it's not a mistake. And that's because we're going to do some rewiring of your brain in this unit, to be honest. Your brain is a mess. Your brain has a bunch of stuff in it that you've learned since childhood, and that stuff is a combination of two different things. And what we have to do is we have to weed out the bad stuff. Here's the combination of things that's in your mind. You've got a bunch of stuff in your mind about numbers, and then you got a bunch of stuff in your mind about base 10 numbers. And those two things are inextricably linked, although we're going to extract them, right? They are tangled up in your mind. You've got so many different things that have to do not with numbers per se, but which has to do with base 10 representations of your numbers. And what we're going to do basically in this lesson, in this whole episode, is we're going to weed out the bad stuff. We're going to help you break those bad habits so you can see numbers how they really are, okay? As Yoda would say, you must unlearn what you have learned. Okay? And that's what we're basically going to be doing in this unit, is getting rid of the stuff in your brain that shouldn't be there, right? Let me just take a note to start off about the word decimal, first of all. I'm going to be using the word decimal and talk about decimal numbers. Now, normally when people hear the word decimal number, they immediately think of something like a number with a decimal point in it, right? And they say, 3.496, that's a decimal number because it has a decimal point as opposed to an integer, okay? That's not what we mean in this lesson when we talk about decimal numbers. When I say decimal, what I mean is a base 10 number. And if you don't know what a base is, we'll cover that. But essentially what that means is a string of digits that is expressing a number, and those digits should be interpreted as powers of 10. That's what we mean by a decimal number. And when we talk about an octal number or a binary number or a hexadecimal number, all we mean is a string of digits that is expressing a quantity in some other base, right? It's really actually a misnomer. They shouldn't be called decimal numbers and hexadecimal numbers because a number itself is not intrinsically decimal or hexadecimal or anything else. A number is simply an amount or a quantity, right? And that's actually where we're going to start right now, is talking about what a number is and what a number is not. So I've entitled this first segment, What is a Number? Which again sounds like about the most basic thing you could ever have in a math class, let alone a college math class. But I'm going to tell you what it is and what it is not. A number is a quantity or an amount. That's what we mean by a number. It's an amount of things. It is a quantitative value, okay? Now, that may seem obvious to you, as plain as the nose on your face, but let me tell you what a number is not. A number is not, and this is what you're going to think it is, and we have to purge your brain of this nonsense. A number is not a string of digits. And that's what we're accustomed to thinking about a number is. When I say 347, if we see that written down on a piece of paper, we say, that's a number, right? 347 or whatever. And it's very, very easy for us to confuse the quantity, 347 things, with the string of digits 347, which is a compact way of expressing or writing that quantity. But as we'll learn in this unit, that is not the only way of writing out that number. And in fact, the writing out part is really misleading. And again, those two thoughts are so inextricably linked in your head that you almost, we're so brainwashed to think in terms of 10, right? Because we have 10 fingers. God gave us 10 fingers, and that's undoubtedly why we do everything in decimal. But we're so hardwired that way, we're so brainwashed that we almost can't think of the number as anything else except the string of digits. We think of the string of digits as being the number instead of being a representation of something much more fundamental, which is a quantity or an amount. Here's an illustration for you. There was not too long ago, one of my students came into my office and he was having trouble with his, I think it was operating systems class or computer architecture class or whatever. And they had to do some things with hexadecimal, and we'll learn what hexadecimal is later in this unit. And he was saying, Stephen, I need some help here with my C code. I have in my C code this line here, int x. So I've defined an integer, and what he asked me was, he said, how can I convert that into hexadecimal? Because I need to print it out in base 16. How can I convert that number into base 16? That's what he asked me. Now, I knew, of course, what he meant. What he meant was, how can I print it in base 16? And that's the question he should have asked, right? But here's the thing. You can learn a lot about a person by the questions they ask. And I uncovered, and that sort of question belied a problem in his thinking, a particular flaw. And here's what the flaw was. When he said, how do I convert that integer named x into hexadecimal, really that implied that he thought that the number was decimal to start off with. He thought the number x was intrinsically a decimal number, and so he was asking, how can I convert that to hexadecimal? He thought of the number as being base 10, and he was saying, how can I convert it to base 16, right? Here's the news flash, and he probably thought, hey, I use an int to hold a base 10 quantity, and he was asking me, hey, Stephen, what do we use? What kind of data type? Is there something called, a hex int that represents a base 16 integer? Whatever, what is that? Here's the bottom line. What do you use to store a base 16 integer? You use int. What do you use to store a base 7 integer? You use int. What do you use to store a base 119 integer? You use int, because an int is not a base 10 integer. It is not a base anything integer. It is an integer. And an integer is a number, a whole number that represents a quantity or an amount, and it is completely free from whatever base we might use to describe that integer. When we write it out, we're typically going to write it out in some base, although I'm going to kind of go back to really, really caveman days here in a minute and get rid of digits entirely. But when we write it out, we typically write it out in base 10 because we have 10 fingers, right? But the number is not intrinsically in a base. And you may already know that, and that may not seem like a shock to you, but most of you watching this lesson, and I'm sure it's true for me as well, trying to beat my head into this topic, it seems like it is base 10. It seems like, when we think about it being, this is how you'd represent it in base 16, we think of that as being like this weird contortion or sort of this warped version of the number. And the real, true number, of course, is the base 10 expression. In reality, nothing could be further from the truth. There is no natural base to express anything in, and it's simply an amount or a quantity, right? So here's the first thing I'm going to do. I'm going to draw some numbers here on the screen. Let me show you how I'm going to draw them. I'm going to say this right here in that box, not the box, but in the box, is the number 0. And I'm going to say right here in this box is the number 1. I'm going to draw just a little circle like that. And in this box, I've got the number 2. And up here, I've got the number 3. And down here, I've got the number 7. Okay? That is what a number is. A number, just think of it as some quantity of rocks or pebbles or diamonds or whatever you want to think of yourself as counting. But a number is nothing more than an amount of rocks. Okay? This here is a way that, in the Western world at least, we often express that quantity. But this thing right here is not a number. That thing right there is a digit. And it turns out that if we have that many in our little sandbox, we, in the Western world, express that with 2 different digits. And that's how we write out this thing right here, okay? But the number is the things in the box, and that is what's important about math. All this stuff about how to write it is much, much, much less important, although we're going to talk about different writing systems and the ones that are principally used in computer science in addition to decimal, which is what human beings typically use. But again, and not to beat this to death, but I think I need to beat it to death to really get this through your skull, because again, all your life you've dealt with base 10 and only base 10, with maybe a couple little rare exceptions in some math class or something, right? And so it's so hard to break that habit, right? Let me give you an illustration that will kind of make this clear. I'm going to write some numbers here. And I'm going to illustrate with this example here why the base that we choose to write a number in doesn't matter. So you will see that I'm drawing some numbers here, and I'm actually going to draw 4 numbers on the screen. And I'm trying to arrange the dots in the box similarly. Okay? Now, those are 4 numbers. Now, what I did when I went from here to here is I just added one. I added another rock. I added, I guess it was that one right there that I was trying to make the new one. Then when I went here, I added another rock, and the one I added was that one right there. And then when I went from here to here, I added another rock, which I think I was trying to make that one be the new one, right? And then we could go on from there. So you can imagine up here, we sort of started, we kind of added one rock at a time to our little collection. We were getting this amount, and then this amount, and then this amount, and then this amount, etc., etc. Now, let me ask you a question. When you look at those 4 boxes and the numbers that are in them, do any of the transitions seem any different to you from the others? Is there any one of these transitions from box to box that stands out as being unusual or unique or different from the others, or do they all seem the same? I think you'll agree with me if you think it through that all those transitions are in fact the same. Every one simply involves adding one. And then to get the next number, we simply add one. And to get the next number, we simply add one. That's all those transitions are. Now, you might say, okay, duh, why are you telling me this? Again, this is something that seems so incredibly basic, that why is it even worth saying? Here's why it's worth saying. Because if you expressed this box as that symbol, and you expressed the number of things in that box as that symbol, and you expressed the number of things in that box that way, and the number of things in that box that way, and kept going like that. If you expressed them like that, and you thought of these things in red as real things, you might be tempted to say, when you go from here to here, that's not really that big a deal. And when you go from here to here, that's not really that big a deal. But my goodness, going from here to here, wow, that was a big deal, man. Something deep and profound happened on that transition that was different from all the others, because we went from only using one symbol to suddenly having to use 2. We are now using pairs of symbols to represent all the boxes after this one, whereas before here we were content with one symbol. There must be some deep, significant effect that happened on that transition. And what I want you to understand is that that is an illusion. There is nothing different that happened going from here to here that didn't also come on the other ones. It is a completely arbitrary point at which we decided to roll over our odometer and say, you know what, we had a symbol, and then we had another symbol, and then another one, and then another one, and then another one, and then another one. We had to keep coming up with more crazy ones, and another one. How about something like looks like that? And now, I don't know, how about something looks like that? And now another one, how about that? And then another one. I'm sick of it. And the point at which we said we're sick of it, and we said now we're just going to reuse the symbols that we have, and let's just use these 2 together, which we've already had. From now on, we're just going to reuse our symbols. The point at which we reused our symbols is, I promise, completely arbitrary. Almost completely arbitrary. I mean, like I said, we have 10 fingers, and that's undoubtedly why we chose, back in, the day, to stop our symbols at 10. And there's going to be reasons in computer science that we stop at 2 or at 16 or sometimes at 8. But I want you to understand that the numbers themselves, nothing magic happens at those boundaries. The numbers simply add one, add one, add one, add one, all the way to infinity. Nothing different is happening at that boundary. And that's the first and most important thing to understand. If you really, really get that, almost everything in this episode is just going to fall into place. That's the one stumbling block where we just can't get over thinking that something magic has got to happen at 10, when in reality that's an arbitrary number. Okay? Let me kind of finish this up by giving you some things that have to do with numbers, right? So there are some concepts, many concepts, things that have to do with numbers, not strings of digits, mind you, not representations of numbers, but numbers. Here's one. Consider the word even. If we talk about a number being even, let me draw a number right here. Question, is that an even number? And the answer is, yes, it is. And here's why. Because I can make pairs of things, and I have none left over when I do. And that's why that number of rocks is an even number. And if I had added one here, it would no longer be even. And if I added another one here, it would be even again, okay? Now I know this is so unbelievably pre-kindergarten basic, okay? But the key thing to understand is that it's not because the digits are even, or because the last digit is even, or because there's any trick we know for looking at a large number written out in decimal form and figuring out that it's even. None of those things make it even. What makes the number even is the fact that you can divide it into pairs and don't have anything left over. That is a number concept, not a string of digits concept. Okay? Here's the next one. What if I talk about greater than? I'm going to make a number here. I'm going to make a number here. And I'm going to say, is it true that this number A is greater than the number B? And the answer is yes. And the reason is, if I pair these up, 1 for 1, 1 for 1, 1 for 1, I run out of rocks in the B box before I run out of rocks in the A box. And that is what it means to say that A is greater than B. Greater than is a number concept. It is not a base concept. Now, I know we know these tricks. If I give you a number written out in decimal form, and I give you another number written out in decimal form, and I ask you if one of them is greater than the other, we all know how to do it, right? If one of the numbers is negative and the other one is not, the positive one is greater. If they're both positive, then we look at how many digits it is, and the one with the greater number of digits is greater. And if they have the same number of digits, then we look at the leftmost digit, and whichever one is greater in the leftmost place is the bigger number. But if those are a tie, then we go to the next place and the next place and the next place all the way down the line, right? That is the rule about how to determine whether two numbers expressed in base 10, or it turns out in any base, are one is greater than the other. That's our rule for doing how to do that. But I want you to understand that's just all a trick that we learned because we're so accustomed to dealing with numbers in base 10. Really, greater than doesn't have anything to do with any of these rules between which symbol is greater than another or how many decimal places there are, or any of that kind of stuff. What matters is how many rocks are in each box, and whichever box has the most rocks is greater. Okay? Here's another one. What if I asked you, is a number prime or not? I'm going to draw one here. Is that number prime? And the answer is yes, it is. And why is that? Because there's no number in which we can take out that many and end up even, right? If I try to take 2's out of this thing, it doesn't end up even. If I switch gears and say, well, what about 3's? Can I take groups of 3 out of this thing? Doesn't come out even. If I say, well, let's take out groups of 4 out of this thing, it doesn't come out even. And if I take groups of 5 out of this thing, it doesn't come out even. And no matter what number I try to take out of this thing, none of them comes out even. Therefore, we say it is prime. Prime is a number thing. A number is prime or not a string of digits. String of digits is just a way to print a number. Now, here's something that is a digit thing, right? What if I asked you, is a certain number a 2-digit number? Now, let me draw one here. And I said, is that number right there a 2-digit number? And I'm here to tell you that the answer to that is don't know. Don't know unless you tell me what the base is. If I were to express the contents of this box in base 10, I would express it with 1 digit. Therefore, it is not a 2-digit number. And if I were to express the contents of that box in base 16, it would be written like that, which is also a 1-digit number. If I were to express the contents of that box in base 2, believe it or not, it would look like this, which is a 3-digit number. The number of digits that a number has is totally dependent on the base that we choose for writing it down. Therefore, there is no such thing, really, as a 2-digit number. It's simply not a concept that applies to numbers. That's a concept that applies to strings of digits. It applies to representations of numbers. Now, of course, what we mean most of the time when we say, hey, a 2-digit number, when your kid turns 10 years old and you're all excited and you have this big birthday, you're double digits now, right? That is simply a way of saying that in decimal it's a 2-digit number, right? But again, that's not a property of numbers. That's a property of representation systems. And here's the interesting thing, which you probably know, but just realize this. Mathematicians, many of them, study numbers, right? Numbers is obviously a big thing in mathematics. Numbers are important, and most of the things that we study about numbers, greater than, less than, equal to, even, prime, all that kind of stuff, most of those things are in fact properties of numbers. And the fact that we have little, helpful tips to figure out how to tell whether something applies in a particular number system like base 10 is really just a little handy trick. But the underlying statement is about the numbers themselves. All right, so get ready for this episode. What I need you to do is try to erase from your brain a lot of the things that I try to help you relax. And you're going to grip onto them, man, because you remember memorizing those times tables, baby. And you remember 7 times 7 equals 49. And it took you forever with flashcards to beat that into your brain. And now it's going to seem like I'm telling you, throw all that away, right? Because all that's base 10 stuff. And of course, most of your life you are going to deal with base 10 because you're a human being on planet Earth. But in computer science, we often have to deal in other bases, and they're really not that hard as long as we can get over our base 10 prejudice.